we're sticking with 5.1, looking at some additional identities. I wanted to go back to the unit circle for a second, and if you'll recall that we determined way back when that the adjacent side of this triangle, the x value, is your cosine, because it's always going to be like your adjacent over your hypotenuse, and in the unit circle the hypotenuse is 1, so it just ends up being that adjacent side. That's the cosine, and the y value is the sine. If you look at this, aside from looking at that ordered pair there, but you just look at this as a right triangle and do a little Pythagorean theorem on it, where you take one leg squared plus the other leg squared and it equals your hypotenuse squared, we would come up with this identity here, and saying just that the sine squared plus the cosine squared should always equal 1. That's an important identity right there. It's called the Pythagorean identity. And because there's so many relationships between the 6 different trig functions, I could rearrange this a little bit, play around with it, and come up with other identities. For instance, sine squared is just 1 over cosecant squared. And then, if I tried to get rid of the fractions here, I could multiply everything times that cosecant squared theta. And that's what I'm going to do here. Take every term times cosecant squared theta. Here it's going to cancel, and I'm just going to have a 1 plus, this one's going to be a cosecant squared times a cosine squared. And it's going to equal cosecant squared theta. And then I want to try to simplify this up a little bit, and remember that cosecant is really just the 1 over sine squared. I could look at this cosecant as a 1 over sine squared times a cosine squared, and that would multiply together as a cosine squared theta over a sine squared theta, which in turn is really just cotangent squared theta. And what we managed to do there is create a new Pythagorean identity using different trig functions. That means I have this one up here, and I have this one down here. I have 2 of them. And to be honest, you could come up with another one. Right here at the very beginning, instead of turning this sine into a 1 over cosecant, I could have turned cosine into a 1 over secant and done the same business and come up with a different identity, and it would have looked like 1 plus tangent squared theta equals secant squared theta. Those are our new identities today. They're called the Pythagorean identities. There's 3 of them. They're paired up differently. The sine and the cosine go together. This is probably the most common one, but we will use the others as well. Just look for kind of a pattern here. It's always a 1 plus a tangent squared is going to equal, and I guess I always remembered that the cos go together, the cotangent with the cosecant, the non-cos, the tangent and the secant, go together. But notice that the 1 is in a different place than where it is on the original. The 1 is by itself, but on these other ones, the 1 is with the tangent. And you're going to also see these in different orders. Rather than having always the 1 plus tangent squared theta, you could subtract tangent squared on both sides. And you may see this as an identity like a 1 equals secant squared theta minus tangent squared theta. The thing is you have to be familiar enough with them that you notice it when it's sitting there in a problem. One of the key things that you'll look for is that it's squared. A lot of the ones we were doing yesterday, didn't have to be squared. If you see 2 trig functions together and they're squared, good chance you could create a Pythagorean identity with it. So using these 3, and these again are ones that you would definitely have to know, The other thing, I guess I already addressed this part right here, but this is important, that for the Pythagorean identities to work, they have to be squared. You can't like square root everything and end up just a sine x plus a cosine x equals 1. That is not the case. So always squared. Let's try using those. We're going to use some of the things we did yesterday along with these new identities. Let's look at this first one. Okay, so I have a cosine squared, but I only have one cosine squared. The sine is not. One of the things that we can do with trig functions, just like we could if these were any other regular algebraic functions, is that we could do some factoring. If I look at this term here and this term here, they both have a sine x. Let's go ahead and factor out that common factor of sine x. And then you'll have left cosine squared x minus 1. Now all of a sudden, I have this cosine squared matched up with a 1, and I'm thinking, oh, I could rearrange a Pythagorean identity to make that work. If you'll recall, I'll write it down here lower. Remember that we had sine squared theta plus cosine squared theta equals 1. And if I subtracted, well, here's really what I probably should do. I'm going to get the cosine squared by itself, so I'm going to subtract sine squared theta on both sides. So that's going to cross off. There's my cosine squared. But meanwhile, I'm also going to subtract 1 on both sides. So this 1 and negative 1 cancel out. And here I have my, I'm going to have to work up. Sorry, I didn't plan ahead on this. Cosine squared theta minus 1 is equal to a negative sine squared theta. Okay, this right here matches this. I'm going to replace that then with a negative sine squared x. And if I have a positive sine x times a negative sine squared x, I'm going to have a negative sine cubed x. Simplified down to one trig expression. All right, our second example here looks like we have a couple reciprocal identities. I could take this 1 over sine squared alpha, bump the sine squared up and call it a cosecant squared alpha, minus, I could bump my tangent squared up and call it a cotangent squared alpha. And now I see that I have these squared identities, and they're the two that match together. The cos go together. So I know the thing that's missing is a 1. You do have to be careful that it matches up correctly. So I'm going to come down here to the bottom again. I'm going to start a little higher. I remember that it's a 1 plus cotangent squared, I guess alpha or theta or whatever you want to use, is going to equal cosecant squared alpha. And all I got to do is subtract cotangent squared alpha on both sides, and I'm going to have this right here, cosecant squared minus cotangent squared. Those would cancel, and I'd be left with a positive 1. Sometimes it ends up being a negative 1. You really have to pay attention to your signs. This one came out really nice. All right, now on that previous problem, this says it's a new strategy, factoring. Well, we actually kind of already tried that factoring. On this one, well, there's a couple ways to look at this. This secant squared theta minus 1, I don't think I'm really ready to worry about factoring because I think it's sitting there for me. You have to look back at those identities. It would probably help because I'm not going to rewrite them every time, but if you look back at your Pythagorean identity that involves a secant squared, well, if you take the 1 over to the other side, what you should be left with is just a tangent squared theta. There's no real solving to do on this one or simplifying. That is the identity right there, just rearranged. Be looking for those to be rearranged sometimes. On this next example, this is what we're talking about, how you might have to factor. If you look at this, it's a trinomial. There's 3 terms to it. And notice here that this is a squared term, whereas this one is not squared, and this is just a constant. This expression right here is really very similar to a 4x squared plus an x minus a 3. This tangent theta value here is like your variable. Tangent squared is an x squared. And this would be something we could just factor. 4x and 1x, 3 and 1, you'd have a positive 4x, negative 3x. And then we could solve from there or simplify anything that we wanted to. All right, that's what we're going to do right there. We're going to do some factoring. So ignoring the x's, and let's go back to the tangents, instead of it being a 4x in my parentheses, it's going to be a 4 tangent theta. It's still going to be a minus 3. And then over here, I'm just going to have a 1 tangent theta plus 1. Now that doesn't look necessarily any prettier than where we started. And I'm not sure there's any place to go with this. It's just an expression being multiplied by another expression. Can't do anything with this because it's not squared anymore. We're really done. On this slide, I'm really just showing you how these things factor. Not necessarily, this wouldn't be our end goal. This is getting us ready for something in the future. If we look at number 5 here, this one, looking to factor, let's practice the factoring skill. I'm going to go ahead and look for a common factor on this one. Since they both have a cosecant x, I'm going to factor that cosecant x out. In this first term, if I factor one of them out, then I'm still left with a cosecant x minus 1. And again, this is getting us ready for something in the future because really I'm done on that. It'd be nice if that was squared, but it's not. I'm just practice factoring. And that actually makes me go back. I wasn't thinking on this first one because really we are just practicing this factoring. These answers aren't going to be pretty. This number 3, this would be a great way to simplify it, but I want you to also look at it as though it was something you could factor. It would actually be a difference of squares. The first term's a squared, perfect square. 1 is a perfect square, and we're subtracting. You could factor that as secant theta plus 1 and secant theta minus 1. It was just too tempting to just call it tangent squared x because that's what it is, but for what we're doing in the future, maybe look for this to be a difference of squares sometimes, and that might be something you can work with. All right, so what do you think on number 6 here? What would you do with this? We just keep adding options here. So we've done the reciprocal identities. That might be something we can try. I don't see anything squared here, so that kind of leads me away from doing anything with a Pythagorean identity. But you have your reciprocal identities, your quotient identities, and now your Pythagorean identities. And those are the 3 things. Don't ever just sit there and do nothing with it. Try something, change something out. When I look at this, I'm probably going to get rid of the cotangent x. That's the one I want to be rid of. I'm going to change cotangent x. It's not going to help me to do the reciprocal where I call it 1 over tangent, but it would help me to use my quotient identity. And it would help if you had your identities sitting right there. Really, it'd help if you knew them off the top of your head. But have them someplace handy because cotangent x is really cosine x over sine x. And that's going to get multiplied by cosine x. I guess I'm going to go ahead and put it over 1 so it's all together. This is the second part of that. The sine x on the front end is just going to stay there. Now let's look at what happens. You have a sine x plus cosine squared x over sine x. Now, this kind of leads us into what we're going to be doing up here, where we have these fractions, and we're going to try to combine those fractions? Well, to add them together, and so right now this is over 1, to add them I need to get a common denominator. It appears that my common denominator on this example will just be sine x. On the left, I have to take it times sine x, and on the right, I already have that. This will become sine squared x plus cosine squared x over that common denominator sine x. And then hopefully, this is jumping out at you right now, thinking, oh, okay, that's one of my Pythagorean identities. Sine squared x plus cosine squared x is simply 1 over sine x. And as a last step, let's go ahead and just get rid of the fraction. Let's bump sine up to the top and call it cosecant x. Final answer. That worked out really nice, but it does take some work. Don't be afraid of work. It's all right. Let's try number 7. This one also adding two fractions. Let's get a common denominator. It's not as pretty, you can tell, but that's all right. We can do it. Looks like on the right, I'm going to take it times 1 plus cosine theta. On the left, I'm going to take it times sine theta. I end up with then sine squared theta plus, and here I'm going to take and distribute my cosine theta through the parentheses. And it's going to be all over my common denominator. 1 plus cosine theta times a sine theta. No reason to try to distribute that yet. Let's wait and see. We usually wait to see if something would reduce. Hopefully what you notice on this, remember right here, this sine squared plus cosine squared, we kind of have that going on right here. There just happens to be a cosine in between it. That's okay. I can grab this and that and call it 1. Plus the cosine theta will still be sitting there. Do you see how nicely this is going to work out for us then? Right here, we have a 1 plus cosine theta. We have a 1 plus cosine theta. Those get to cancel, and I'm left with a 1 over sine theta. It's like deja vu here, just as cosecant theta. That's all I've got for you right now. I could sit here and do problem after problem. Every one of them can be different. You have to be looking for strategies, and you have to know those identities, and those are the things that will give you options on how to set problems up. Study your identities, and then good luck on your homework.